that was weird. I take it all back. I love governments. They're really nice people. They do everything perfectly well. I have never seen them ever tell me a lie or do anything bad. Phew. That was close. Okay. So I've written down a lot of questions. I'm not sure if I'll actually get to them all. But, you know, it's a kind of idea of how to find partial derivatives. I'll start with my first one, which is a version of question 7. And what we're doing is making them more and more difficult. I am going to do the partial derivative with respect to x. Now, when you look at this, what you should see is a product rule. Can you see an x squared times this guy? Not only is it product rule, would you agree this guy here is a chain rule as well? So if you call this guy f and you call all of this g, the product rule is that. Now, with respect to x, when you differentiate this guy, you get 2x, and you leave the other piece alone. Add, you leave the first one alone, and then you differentiate this. Well, this is the chain rule. It's essentially something to the power of 4. So it's 4 somethings to the power of 3, followed by the derivative of what's inside the brackets with respect to x. So that guy gets you 1, and differentiating xy squared gets you that guy. Are you comfortable about that derivative? Right, now you should always make things look pretty, right? Style points. Factor, factor the heck out of it and make it look like the original. Now I'm looking at this term and I can take out a common factor of cubed. I have an x squared and an x here, so I can take out a common factor of an x. That leaves me with 2 lots of this guy, plus, oh, too late now, but I'll do it later, 4x of this guy. And if you distribute this, you get 2x, 2xy squared, you get 4x, 4x, y squared. Those two get me 6x, and those two get me 6xy squared. I can pull out a 6x. And if you pull out a 6x, you get 1 plus y squared. Right. Most of what you end up doing is algebra, right? Just making things look nice. Okay, let's try a version of 9. Okay, what do you want me to do? U or V? Because the one you choose is going to be slightly different looking math. What one do you want? U or V for 9?
V.
Okay, so we'll use that notation. That's a top guy, call him F. That's the bottom guy, call him G. Since both of those have V's in them, it is a quotient rule. And if you differentiate the top with respect to V, you leave the bottom alone. You leave the top alone and you differentiate U plus V to the 4. That's just a number, right? It's treated as a constant. So that gets you 0 and this guy gets you 4V cubed. And then the whole thing is over U plus V to the 4 squared. What I would do now is pull out an e to the v as a common factor. And call it good. And that would be the answer to that fella. Now, if you want to do a version of 10, let's do a derivative with respect to theta. Well, it's 8 sine of something, so it's going to get you 8 cosines of something. And then you differentiate, because it's essentially a chain rule, what is inside the brackets with respect to theta, and that gets you a negative r sine theta. And then I'll try and make that a little bit pretty. Negative 8, put the sine before you put the cosine. Going a little bit quick here, but are you comfortable with the process? Isn't it really just Calc 1 with a little twist on it?
Isn't there an R in there?
Say again, Molly.
Isn't it like negative 8R?
I missed it. R, you're right. There it's fixed. Okay. Now this one has problems, and I'm going to do both versions. And you might think, what is the problem? It's the fact that one of these variables is a power and the other is a base. And you might think, well, does that make any real difference? It actually does. You have to understand, a good imagination, you have to understand that this is really x to the 42th power, right? Or x cubed or x squared. Isn't it x to a constant amount? So when I differentiate this with respect to x, I'll do exactly what I would have done if it had been x to the power of 4. Won't you multiply by the power and reduce the power by 1? Do you see how weird that looks? But it's correct. Are we good with that one? Now, even weirder. X to the power of 4y. If you consider the y as the variable, isn't this like 2 to the power of 4y, 7 to the power of 4y, 42 to the power of 4y? So if you do 2 to the power of y, right, 2 to the power of x, whatever let you want, right? Isn't the derivative x to the 4y, like 2 to the y, right, x to 4y, times what? If I had asked you to differentiate that guy, your answer to its derivative would be 2 to the power of 4y times log 2. Agreed? And what about the 4y? What would that also get you? It's a little baby chain rule. Times 4, right? Times an extra 4. Now look, this guy, right? Differentiate it. X to the 4y times what? Times the natural log of the base. Times what else? Times the derivative of this. Do you see that? 4. That's what makes that one such a weird looking answer. And that's pretty much a snapshot of finding first partial derivatives, right? I'm sure there's other exceptions, you know, product rules with quotient rules inside them or whatever, but we've got the gist of that. So the next two questions are not actually too bad. We're just going to up the number of variables that are in our multivariate function. So essentially there are 3 variables. So f is a function of x, y, and z. But you stick to your same basic thinking. And your thinking is, one of these guys is a variable and everything else you treat as a constant. So if you want to do the partial derivative of f with respect to x, Don't you just go through these and say, okay, x is a variable and treat everything else like a number. So if I wanted to differentiate this, you would get 7 x to the 7. And wouldn't the y and the z squared still be there? Because it's like a multiple of x's. And I just made a mistake there. Did anybody notice what I just did wrong?
It'd be to the 6.
Now it's fixed. What would 5yz get you if you differentiate it with respect to x?
0.
Right, so I won't write it down. Now, if you do it with y, this guy here is the only variable in town. So that's a bit like 5y. So when you differentiate it, are you happy about the x to the 7 z squared? And then if you take this term, it also contains, but it's just a y. So if you differentiate this with respect to y, are you happy about where the 5z, I should say, came from? And if you do it with z's, if you differentiate this with respect to z, you get 2 x to the 7y z. And if you differentiate this with respect to z, you get 5y. Have you noticed that, as always, the three answers are quite different looking, which is typical. Are we good with that one? Couldn't you basically have a 20-dimensional function and find 20 different partial derivatives? It really wouldn't, the process wouldn't change that much. So 15 has got 4 variables in it. And it's x to the 6y, the cosine of z over t. Now, I'm not going to do all 4 derivatives, but let's do these two. Let's do that one first. So x to the 6, y, and that t are all considered as constants right now. So when you differentiate this guy cosine of the fraction, you get this guy. About a negative. But I also get something else. Isn't there a little baby chain rule going on here? And if you take z as your variable, isn't this like z over 2 or a half z kind of thing? So can you see that you get an extra 1 over t? So if you differentiate this expression with respect to z, you get negative x to the 6y sine of the fraction times the derivative of this fraction with respect to z, and the derivative is 1 over t. If, however, you do this guy, you get negative x to the 6y sine is z over t again. But you finish with the derivative of z over t with respect to t, right? Z over t with respect to t. What's that going to look like? You know, like 5 over t with respect to t, that kind of thing. What would you get if you differentiated it?
Negative z over t squared.
Correct. And then I'd probably tidy this one up a little bit. Positive. Probably make it look something like that. Okay, so that's first partial derivatives taken care of. Any questions before I move on? You notice you have to keep track of who's the variable and how to treat the other letters. And sometimes you miss it if you're not careful. Okay, let's look at second derivatives. Well, you know you can find first derivatives. You should be able to find second partial derivatives and third partial derivatives. The good news is you don't change anything. Would you agree to get the second partial derivative? Shouldn't you just differentiate the first partial derivative with respect to whatever the variable happens to be, in this case x. So it's going to start off looking exactly what I just said. So there won't be any surprises for the first couple of examples. And then I'm going to throw a spanner in the works. Let's do the partial derivative with respect to x. Well, so you get 6x to the 5y squared, take away 3y cubed plus nothing. You agree that doesn't surprise us? That's what it always was. Now, the notation for second derivative is that guy. That's why I kind of like that notation. Now, you differentiate again with respect to x, so that's multiplied by the power and reduce the power by 1. And would you agree that's nothing? And I could do a third derivative, multiply by the power and reduce it by 1. No surprises. You agree that's kind of intuitive, that makes sense. Second, third derivatives. Now, notation gets a bit clunky here. That one's pretty obvious. And this one here looks like that. And this one here looks like that. Can you remember second derivatives looking like that in Calc 1? You see the twos go in slightly different places, right? There's reasons why it is what it is. But just in case someone says find that, well, you realize it's just a third derivative. Now, the spanner in the works. I've already found this guy, so I'm just writing it down. What do you think I'm asking you to do now?
Cure cancer.
Say again, Will?
Cure cancer.
You think I'm going to ask you to cure cancer?
Well, it'd be good if we did.
Yeah, well, I already did that, but it was too much work, so I just didn't publish it. So since I don't have that one as one of my choices, what mathematical choice do we have for this one?
I mean, I'm assuming that you'll just take the first derivative, partial derivative for x, and then just take the partial derivative for y.
Yeah, that's exactly what you do.
Cool.
So you take this guy and you find its partial derivative with respect to y. Which is not something you would have thought was worthwhile doing. Why would anyone want to find a partial derivative with respect to x and then change it and then do a different, the next partial derivative with respect to y? But strangely enough, these things are actually quite useful. They do actually help you in the geometry of 3D space. So there are reasons for calculating them. Now, I'm going to start with this guy, and I'm going to do its partial derivative with respect to y. Well, if you differentiate with respect to y, you get 2x to the 6y. If you do this with respect to y, you get negative 9xy squared. And if you do this with respect to y, you get 1. And now I'm going to do that guy. So you differentiate this guy now, but with respect to x. And when you differentiate this guy with respect to x, you get that. And when you differentiate this guy with respect to x, you get that. And when you differentiate 1 with respect to x, you get 0. And you have that. Do you notice something remarkable here?
They're very similar. Are they going to be the same if you have the partial derivative of x then y and partial derivative of y then x?
Yes. Now, Yeah, they are. They're actually identical, which is amazing. Because our experience has been, hasn't it, that when you do a derivative with respect to x and then you do a function with respect to y, you typically get quite different looking functions. And you'd expect if you went into the second derivatives, they even look more different, right? Isn't an fxx probably quite different than an fyy, right? And they are. But this combination is the same. And it's a guy called Clairaut. I believe he's French. And it's called Clairaut's theorem. What essentially Clairaut's theorem says is that that derivative will equal that one. So can you imagine you may get a homework question where you're asked to find 4 different answers, right? That one, this one, and that one. If you find this answer, can't you just write that one down because it's the same? It's maybe not a lot of work, but isn't it at least saving you somewhat? Now, Clairaut's actually got a little restriction on that, and it's a very interesting one. This is true, provided that the function that you start with is continuous, right? So there can't be any weird vertical asymptotes going on, right? You remember we did when is a function continuous. So you really want to be careful if there's some weird vertical asymptotes or undefined values or something, right? Because then Clairaut's theorem will break down. And in fact, we can use that as a proof that you've got a continuous function. You find these guys separately, right? You just do them by calculation. And if they end up being equal to each other, Clairaut's theorem says that must mean that the functions are continuous everywhere.
Is that the converse of Clairaut's theorem?
Yes, you would reverse the A gives you B, B gives you A, right? That's called the converse when you're allowed to do that. I think that's a very powerful result. Clairaut also found out the following is true. Do you notice that those are 4th derivatives? And I'm saying that all those guys and others that I haven't bothered to write are all equal to each other. And the reason why they're all equal to each other, don't they all contain 2 y's and 2 x's? So you differentiate twice with an x and you differentiate twice with a y. And Clairaut says, I don't care what order you do it in. If the function is continuous, I don't care what order you do it in, all of them are the same when you're finished.
Does this also work for 3 variables, 4 variables?
24 variables. That is a very interesting result, because what it allows us to do is we can imagine continuity. Can you imagine a 3D surface? It's kind of obvious to know when there's a problem, right? Can you imagine one of those 3D vertical asymptotes? You could look at it and say, I can see that that's not continuous, at least in certain places. Can you imagine a 10th dimensional function? It might be a bit hard to figure out if it's continuous or not, because you can't even visualize it. But couldn't you do a Clairaut test on it? Can you just find x, y, and y, x, y, z, w, and w, z, x, y? And if they end up being the same, hey, I can't see it, I can't draw it, and I don't even know what it is, but I know it's continuous. Right. So it allows us to have a, it's a really cool thing to do. I like it. Called Clairaut's theorem. Let's do a version of 19 then. And it's a natural log of ax plus by. And we'll just do some of the partial derivatives. Let's find the derivative with respect to x. Well, that's going to be 1 over ax plus by, right? Times what? Think chain rule. What do you get if you differentiate this with respect to x? Times what?
A.
Yeah, just times a. Now, if I do the partial derivative with respect to y, Can I just jump right to the answer? Are you comfortable that that's what the answer would be? Right, if you differentiate ax plus by with respect to y, don't you just get a b? Now, if I wanted to do, or wanted you to do the second derivative with respect to x, we would write that. Now, if you want to do this guy as a second derivative, you might want to think about rewriting it like that, in which case you could do it as a chain rule. And if you leave it like that, you could do it as a quotient rule, but that's uglier. So writing it like that means you multiply by the power, you reduce the power by 1, and then you differentiate what's inside with respect to x, which gets you another a. And this fella gets you negative a squared over ax plus by squared. Are you happy about that answer, where it came from? Now I'm going to cheat a little bit. I already know this answer. And I'm going to rewrite it like that again. So I'm basically copying that line. That's the notation. I know it's a bit clunky, and that's why I prefer that notation, right? You see that one there? Right. So that notation is actually wrong. I apologize. But it's easy to see why I made the mistake. Do you notice that the x and the y are different in these two notations? Technically speaking, this guy is the derivative with respect to y of that guy. That's what we're doing. Now, when you write it like that, is it a little bit clearer why the y ends up being first, even though it's the second thing you're going to do? I do not like this notation because I already did it. Do you see how easy it is to get them in the wrong order, even although I know what you want? Would you agree it's much easier in this notation? Do that first, do that second. In this notation, do this first, do that second. For instance, if I asked you to do this guy, and let's write my 3 again because it looks weird. We would start with the function f. What would I differentiate it with respect to first? Which variable?
Y.
Do you see you do it in that order? Now, if I write it down, I mean, isn't that just natural to us to read from left to right? So that's what it looks like in this notation. That's what it looks like in that notation. Now, the reason why I'm being pernickety about this is, can you imagine that you're going to get a question where it doesn't say find all the answers? It only says find one answer. Don't you have to know which one you're talking about? At least you have to know what order you do it, because it could, it could go wonky on you. Right, so back to my guy up here.
Wait, so for
Yes.
that, if you use Claros theorem,
It will be
couldn't
the
you
same
just-
answer.
Yeah,
Yes, but isn't Clairaut provided the function is continuous?
right.
Which means sometimes the function's not continuous, in which case Clairaut's theorem doesn't work. Right.
Okay.
So if I was looking at a function and I wanted to use Clairaut's theorem, I would say, use it here. Would you agree this function has no problems? Clairaut's theorem will work fine. Would you agree that the sine thing here, wouldn't the Clairaut's theorem work perfectly fine here? Do you think there might be a problem with the log function? That one I would be more worried about, right? But you're correct. In general, almost every function you deal with is continuous, or at least it's continuous in most of its life, right? There may be a little place over here where it's got a problem, but the rest of it is fine. So back to my guy, if I wanted to take this fella and do that second derivative to it, I would multiply by the power, reduce the power by 1, and then differentiate with respect to y, which would get me that fella. And so my answer would be negative AB over AX plus BY squared. Let me show you a little trick. Let's suppose that I will have that function. And I was asked to do the following. To find a fourth partial derivative with 2 x's and then 2 y's. Okay. We'll make the assumption that this function is continuous, which I'm sure it is, right? I can't see any values of x where I'm going to have a problem with this. But if I try to do it in the order that it's written, can you imagine how much work I'm going to have to do? Aren't I going to have to do a product rule with x's? And want to then take an answer and do another product rule and horrible thing. Can you imagine how much work? Or I could say, let's switch the order. And so what Clairaut's theorem can allow you to do is that for multiple derivatives, right, where you're differentiating 2 or 3 times, that you can choose the order in which you wish to do them, provided you make the assumption that the function's continuous. Now, if I do it in this order, 1, 2, 3, 4, let's see what we get. Differentiate this guy with respect to y, and you just get 3y squared. Differentiate it again with respect to y, you get 6y. Differentiate it now with respect to x, you get 0. And differentiate it again with respect to x, you get 0. Do you see the answer ends up being 0? Would you agree that was much quicker than doing it in the order x first, x second, and then y third and y fourth? Does that make sense? That sometimes for multiple derivatives, if you want to choose a different order because you think it's less work, you're totally allowed to, right? Provided the function continuous. Can we just assume that the functions are going to be continuous because they're not going to be nasty to you? Right, let's. Any questions about that before we move on to another situation? Do you like Clairaut's theorem? I won't hold it against him that he's French. He can't help it. To be honest, there was, if you go and look at the history of math, it's quite fascinating. Math, how do you describe this? If you look at science like physics and engineering, the physics of today is like leaps and bounds more advanced than the physics of 100 years ago. Would you agree that the type of things that you can do in the scientific world has just went by leaps and bounds? But mathematics is much slower. The math that you're using right now is pretty much the same math that we were using 100 years ago. And the reason why math is different from science is, isn't science always tweaking and learning and adapting a little bit more and getting a little bit more? Math is more like, we've discovered a truth. And once you found something that's true, isn't it just true? Right? You can't improve on a derivative, right? You found the derivatives, you know how to do them, right? But there were times in history where there was little bumps where somebody came across a cool idea that no one else had thought of. Leibniz and Newton, for instance, figured out how to do calculus. Before that, we never had calculus. We were using, we're actually using Greek mathematics from 2,000 years ago. Pretty much hadn't changed. And then calculus came along, we found, boom, off it went. If you look at the history, there's little bunches of like 50 or 100 years where tons of stuff happened in math. Lots of new things happened. And then it kind of stagnates. There was a time, for instance, when the French were really good at math. And Clairaut, I'm pretty sure, Descartes, Renault, a lot of French mathematicians. It was like the golden age of mathematicians was French. After that, there was a golden age where it was Gauss and Leibniz. Germans, really good at math. Britain had its own. We had Maxwell and Newton, and he did Hamilton, and they had a golden age where they created things. The boring thing is, we're not in a golden age right now. Mathematics right now is pretty stagnant. There hasn't been any real great leap forwards in the last 50 years that I know of. So maybe one day there's going to be some Newton genius that's going to come along and come up with some concept that we never thought of. And then we're going to have a golden age of a whole generation of new people, you know, telling us all kind of cool stuff. And I've drifted, as I do, but we are pretty close to being finished. So put your name down. And when we finish, which we've now done this section, what's left? Well, tomorrow we are going to do the general. And that is us. So